Um, okay, let's let's do a quick recap first. So can you guys see my screen? Okay. So yeah, last time we talked about measure theory, going through the definition of like outer measures, giving an example of how to measure things in the plane using like they call it I think this is called like a pre-measure actually. So this is a pre-measure. And what you can do is you can close it. So you take this outer measure concept and you turn a pre-measure into a measure by so this is the definition of a measure using this theorem. So this kind of tells you this is the criterion for looking at what measurable sets you have, right? And then we talked a little bit about okay, that abstract splitting condition is equivalent to saying, oh, for any set you give me, it's measurable if and only if I can find some open set which contains it, and the difference between those two sets is small, infinitesimally small. Okay. Um, yeah, and then we went over, okay, what does this imply once we have a measure that just is countably additive? One, it respects limits well, and you get things like this Borel-Cantelli lemma. And then we went through a little bit how to look at two measures and compare them. So one way you can look at two measures is if they're kind of disjoint with respect to each other, so they're singular. The other way is if they're absolutely continuous, so they play well with each other. In particular, zero sets of nu implies zero sets of mu. If nu is so mu is absolutely singular with respect to, or absolutely continuous with respect to nu. And yeah, and then finally we talked a little bit about how to take limits of things, take limits of measures. So this is the definition of a weak convergence with respect to measures. Here, what I'm doing is I'm putting in a continuous test function, taking the integral with respect to my measure, and then looking at the limit as n goes to infinity. And if this happens for every continuous function, I say it converges weakly. Okay, and then we went through a couple different decompositions, Jordan decomposition, Hahn decomposition, Lebesgue decomposition, and then finally Radon-Nikodym. And did it, okay, so before I go on, did anybody have any questions about this from last time? Okay, if not, that's perfect. We can move on to the next section, which is about how do we actually measure functions, right? So what we've done is we say, let's work, for example, let's say L of RD. R equals the Lebesgue measurable sets. Measurable sets. Then what we're trying to do is we're trying to look for functions somehow that go from R to R. Let's say they're positive functions and can take the value infinity. And I want to do certain operations to them, right? I want to be able to take integrals in particular. So I need a condition in order to say, when can I do this with f? And the main idea, how you start building these things, how do I construct an integral of just a general function? You do the only thing you really know how to do is just how to take the measure of a single set. So if f is in particular the characteristic function of some set, right, maybe times a constant, I know how to integrate this, right? We should define the integral of f to be equal to constant times whatever the measure was, right? So this is d mu, right? So you can already see, okay, here I need E to be measurable in order to make sense of this guy. So let me just, sorry, let me restrict to, no, I'll keep it general. No, let's do this. Let's make it a Lebesgue measure, sorry. So when I write Lebesgue measure, I'm just gonna write these bars. I feel like that's standard notation. So if I want to take an integral, define an integral of just what's called the characteristic function, I need to be able to define uh, the measure of E. So that's kind of our goal. So the goal is to understand when f can be approximated by simple functions, by simple measurable functions. Simple. So it's this thing, measurable functions. Okay, so that's kind of this whole section. Okay, so how do we actually define measurability? This is a little abstract of a definition, but basically what it says is if you give me any function, right? Let's say I'm some kind of funky function. This is f of x. This is x. What I'm going to do is I'm going to pick a point on the real line called lambda, and I'm going to look at all points which are above this. Let's see. So I'm going to look at this. So that's not actually part of it. So this set of the graph. Okay. And what that is, so the set here is just going to be this guy in R. So I got this squiggle here and this guy. Right, so this is my set. This is my set. Let's call it E lambda. So this is E lambda. Okay, so if this property holds where I look at what are called the super level sets of my function for every lambda, and if I say this is a measurable thing, I can do quite a bit of properties with this. In particular, if I take a complement of this, I know that f is closed under complements, so I immediately get that this guy, so if E lambda is an f, this implies that lots of things are in f. So the set of x such that f is less than lambda is also an f. So this is the sub-level set. I can also put equality if I want by just closing it or taking a limit. Another thing that's also in f is when I evaluated a point. This guy's gonna be an f. And what it does is I squish in I take a lambda above this lambda you're given and one below, and I kind of squish them together. So when I take that limit, I can get that this guy is also measurable. And so on. So any property basically of f is, for example, in some sort of set. So f is in some sort of set O. Let's say O is measurable, O is open. That's going to be an f also. Okay. Any questions about this? How to define measurability? Okay, perfect. Well, let's keep going. Okay, so once I define this notion of measurability, one thing you can do, which is a very weak kind of notion of convergence of two measurable functions, is to consider convergence in measure. So what it says, there's a little typo here, is if I have a collection Fn of functions and f, which is supposed to be their limit, and they're all measurable, then what I can do is I know that because the super level sets of Fn and f are measurable, that this quantity is measurable. So I can take the measure of it. And then I ask what happens when I look at the difference between these guys and ask how many points are above this scale lambda, right? So if you think about it, you want the difference somehow to be close to zero. Something like this. So this is Fn x minus fx absolute value. And when I pick a lambda greater than, let's say this is a lambda, when I'm looking at this set, I want it to be very small, right? As I take lambda to zero. Or so for every fixed lambda, I want as n goes to infinity, this guy goes to zero, right? So this is the limit as n goes to infinity. Should be zero. Okay. Great. Okay, so this is a fairly weak form of convergence. It's different than pointwise convergence. but it's somehow tailored to be about measures. So it'll end up being useful when you consider, okay, how close are these guys converging with respect to a given measure? Okay, so that's definition 7. Another nice property about measurable functions is you can say they're almost simple. And that was the original thing we kind of started with is I wanted to be able to define integrals. So I need simple functions. And it turns out that this condition that every super level set is within F gives you a construction of F as being an increasing sequence of simple functions, Sk. And the way it basically works is, let's say you have, let's say you have a function. It's like this. What I can start to do is I want it to be an increasing sequence of functions. So I'll just start to look at the measure of where F is between 2 points. So I look at F and it's between some interval, right? Of let's say like there's a lambda 1 and a lambda 2, right? That's a measurable set. And what I do is I take the characteristic function of this. And if I want it to be increasing, I want lambda 2. Right. So what this does is, for example, if you give me a fixed lambda 2, let's say lambda 2 is here. This is lambda, say lambda 1 and lambda 2. What I'm going to be doing is I look at the part where F is between these two lines. So that's this region. Right. And then this characteristic function, if I was to graph it, so this guy, what it would be is, okay, it's lambda 2. So actually, I think it should be lambda 1 if it's below. So this is lambda 1. And lambda 1 is just going to be this level, right? So you can see somehow if I was able to pick, so pick lambda I plus 1 dyadic number and take their, so what this means is like they're 2 to the negative n times plus I over something like this, right? So this is what I mean by dyadic. Kind of looks like this. Okay, so the actual construction is fairly simple. You just look at characteristic functions and check that I can measure this and it's measurable. The actual, this is like a, yeah, okay, this gets what we want. Okay, the next theorem we have is another property about measurable functions. And what it says essentially is that a collection of measurable functions is almost uniformly convergent if it converges pointwise almost everywhere. So in some sense, up to small measure sets, convergence pointwise implies convergence uniformly, but up to small measure sets. So the way you can think about it is there's maybe some defect set. So let's say Fn, I know Fn converges to F pointwise almost everywhere. Then what I would like to say is that that these guys somehow converge uniformly. And what uniformly means is that Fn of x minus f of x is less than epsilon for all n greater than or equal to like n of epsilon. Right? So n is just some large number that depends on epsilon. But we can't actually quite say this because it's not true for generally measurable functions since they're not continuous, right? They could just be kind of jumpy. So instead, what you can say is there exists a set F contained in whatever my domain is, E, such that for all x in F, da, 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 let's, yeah, okay. So for all x in the complement. So what I'm saying is f is small. Sorry. Yeah, f is small. So here I actually want that the measure of e minus f is small, is less than some, like another epsilon. Does this make sense so far? It's just, okay, I can upgrade pointwise almost everywhere convergence to uniform convergence by sacrificing a little measure, right? So this whatever the defect is pretty small.
Isn't it the measure of f that must be small?
You're right.
Thanks.
Mm-hmm. And while we're here, might as well. There should be another. Let's do this. So there's too many epsilons. Okay. So for all epsilon greater than 0, for all delta greater than 0. So here's the total statement. I start with something that converges pointwise almost everywhere. Then I know that for every epsilon and every delta, I can find a set F which has small measure, so it's small measure smaller than delta, and I can find an n which depends on delta, such that the difference of these guys is small in this new set where I've taken away something tiny.
Wait, sorry to be pedantic, but should the measure of the set be less than epsilon and everything else is less than delta?
Yeah. Thank you. Okay, does this look better? Okay. I'm basically just like writing this badly in quantifiers. Were you saying something?
Oh, no, sorry.
Okay. Okay, cool. Well, let's keep going. So, so far what we have is, I'll go back. Measurable functions are almost simple, uh, and and they converge almost uniformly. Okay. Now, one other condition which is kind of related to the to this, so E measurable, if and only if for all epsilon greater than 0, there exists an open set containing E. This is open, such that whatever the Lebesgue measure of O set minus E is less than epsilon. So I can contain my E by an open set. Somehow this information that measurable sets are almost open transforms into a property about measurable functions. So this gets property of measurable functions. In particular, what it says is, if you recall kind of the point set topology, I know that F is continuous. F going from R and R is continuous if and only if F inverse of every open set is open for all O open, right? So I pull back open sets. So somehow if I link these two ideas, okay, F, let's say F now is measurable. It's not continuous, but I have this kind of characterizing property that F inverse of every open set is open. And you can kind of imagine patching it together with this condition of measurability, right? I can approximate F by kind of continuous. I can approximate F by things which are like almost open, characteristic functions of things that are almost open. And so in total, what I get is this proof of this Lucent's theorem, which says you take any E in Rn, a measurable set with finite measure. So this one ends up being important just because if things end up going out to infinity, you get bad things. And I need it to be finite valued. So when I take the pre-image, let's say it's positive infinity everywhere. I don't know how to define continuity for that object, right? Actually, if it's evaluated at positive infinity anywhere, I don't know how to evaluate that object. So let's just say it's finite valued. then the measurability condition we had is equivalent to the following statement. Whoops. It says for every epsilon, there exists F in E with small measure such that when I look at F restricted to E minus F, this guy is continuous, right? With respect to the subspace topology. So I'm almost continuous. All right. Any questions about this? Okay. So yeah, this is kind of the end of that section. So the next step we'll be talking about integration. But before then, I wanted to go over problems from last time from the measure theory section. So let's go and do that. I had a few requests over email, but I'm open to questions about them now. If anybody has any questions about this section, about the problems.
Could we please go over problem 2?
Sure. Problem 2. Okay. So let's read through it carefully. Paste. Okay. So this is 2. Okay, so what it says is for any R positive to find this ball. So I have an X, and then I have a circle. And this is going to be a radius R. Okay. And then what I have is E, which is a subset of this unit square. This is Q. With the property that for every X in Q, so you give me an X in Q, and every R positive, there exists a Y within this ball. So I'm going to draw the ball. Again. So for every R greater than 0, there exists a Y. This is Y here. Such that some smaller ball is contained in E, right? So let's say it's a little confusing, this picture with Q. Let's write it like this. So let's say E is some blob. This is E, and it's all contained in Q. Okay. Prove that Q set minus E, so I want to show Q set minus E equals 0. Okay. So let's think about this for like a minute, because I got to think about it. So give me 1 second, and we can think about this problem. Can you guys still see my screen if it's paused like this?
Yeah, I could see your screen.
Just this stuff, the number 2 problem, right?
Yeah,
Okay.
I mean, I could see that.
Okay.
And there's like yeah.
So the one property we have to use looking at this, now that I'm looking at this, is that I have a fixed constant here. So this ends up being, I think, the one important thing. Because if I don't have that, I have no control about how small this ball is, right?
I mean, I have a way to do it, but I think it's using like Lebesgue integration, which is a little bit stronger than I think we need to.
Yeah, I don't think you need to do it using Lebesgue integration. So
Or sorry, differentiation. But
yeah. Let me think about how to, yeah, so you can take a limit. Uh, yeah, I see. No, I don't think we have to do that yet. That is one way to do it. Does everybody know what's called Vitali's covering theorem? No?
is that the one where you like choose a smaller subset of balls and then if you
Yeah,
make them bigger, they
yeah. So let me resume share real fast. So what Vitali, sorry. Whoa. One sec. Yeah, so Vitali's theorem basically says, if you give me any open, so I have a bunch of open balls covering a set, right? What you can say is, okay, I can refine this to be only a countable collection by just growing the number of spheres, right? So let me go back and I'll describe it real fast. Okay. Great. So what we'll need for this is what's called Vitali's covering theorem. Vitali covering. And then we can think about, I'll just tell you what the theorem is, and then we can go from there. So in short, what it says is, if I have a B collection of, so there's a collection of balls, BRX, for some R with some conditions, and X with some conditions, right? So just a collection of spheres. What I can do is, and I have that E is contained within the union of this guy. So B within script B. Let's make this a little clearer. So I use script for if it's a collection of things. So this guy. What I can do is I can find what's called a countable subfamily. B, let's call it B tilde, such that B is contained in, this is just the kind of the use case, 5B, B in. So what this 5 means is I scale up, I'm just scaling up my radius by 5, right? It's 5 times the sphere. Okay, and so what this allows you to do is basically say, okay, without too much loss, I can go from uncountable to countable collection. So countable. Okay. Any questions about that? Okay, so before I move on, does anybody have any ideas about how I would use this?
If you could find for every epsilon, then you have some collection of balls that have total area less than epsilon, that can cover Q minus E. You get that it has a Lebesgue measure theorem. So you probably want to take I guess you start with a collection of balls from some R greater than 0, and just from the problem, and then just take it for every.
Yeah. So let me just write down first. So the collection of balls you're thinking of is the ones. So I'm looking at B. I'm just rewriting what the theorem is, or the exercise. So what did we have? We had that. So this collection of balls around X. So I'm looking at this guy somehow. So there exists, okay, there exists a y and br such that this guy is contained in E. Okay. So what I want to write, I'm just going to write it down and then try and think about it for a second. So I'm looking at this collection of balls such that X is going to be in this difference, right? And so this is now so this guy is a covering of so BRX kind of covers, right? My set Q minus E, which is the one I'm trying to measure. Here I have this. Then what I do is I pick Y such that, and then I look at this set Y is contained in E, right? So I'm using the condition of the set of our problem. Okay. So now there's a few things we can note. One is that well, X is in each of these, and X is in this point. So if I union over this whole collection, so the union of B and B of these guys, this guy contains E, or Q minus E. Right? The one issue though is I don't know how to like work with this, right? Because it's uncountable. I can't take the measure of this and expect to understand it. I can't split across an uncountable number of things. So what I do is by Vitelli, I still get this property. So this is 5. I'll rewrite it like this. 5 times the ball. There exists some subcover. B in, let's call it B tilde. That still contains Q minus E, where this guy is countable. So by Vitelli. Okay. Next, what you want to do is you want to take this. I've now written down, this is kind of the hard step, is to like think about this set. Now what I can do though is take the measure of this. So I know that let me think. So what I want to do is do this. I think that goes the wrong way though.
That looks correct to me.
Yeah. Okay, so okay, maybe we just keep going with this. So these guys are these quantities, right? Hmm. Okay. Yeah, I think, okay. I'm gonna have to go over, this one requires Vitelli in a way that's I haven't thought about in a while. So maybe we go through this one next time because I don't want to like spend too much time thinking about it. So this one actually is quite difficult. It's some geometric condition, and you use vitality to get a subcovering. I'll send solutions after. How about that? Okay. So that was 2. Yeah, 2 is quite hard. Does anybody have any others? I know there was a request for 3 and for 7, which had a typo. So this actually is Q prime. Does anybody want to see this one? Has anybody done this one yet? Number 3? Okay, let's go through it then. Yeah, sorry about that last one. I just don't want to spend too much time on it. Yeah, that one is more of a check on, my guess is somebody was doing a lot of fundamental measure theory stuff that semester and really liked vitality. Okay. Let's do this one instead. So 3. Okay, so if XD is a compact metric space, let's let mu n be a sequence of positive Borel measures. Normally it's written like, let's do this, measures on X. And they converge in the weak star topology to a finite measure, positive Borel measure mu. So mu n converges weakly. Weak star is the same as weak for this, to mu. And then want to show that for all compact K in X, the measure of the compact set is greater than or equal to the lim sup as n goes to infinity of the evaluations of mu n on K. So this is a form of what's called a lower semi-continuity, right? So I'm continuous by taking limits this way. Okay. So let's first unpack what this means. So star, if you recall, it means that for every phi, which is a continuous and bounded function on X, I know that the integral of phi d mu n converges to the integral of phi d mu, and these are all on X. Right? That's just the definition of weak of measures. All right, so can anybody tell me what they would think to do?
Yeah, well, I was looking at approximating the indicator function for K by a sequence of continuous functions.
Perfect. Yeah. So let's try and do that. Let's just plug in. I find this is super helpful. Let's just say I care about this, right? What would this tell me formally, right? When I plug in the characteristic function of this guy on X, this is going to be mu n of K. And I want this to be somehow comparable to this guy, right? So if I take the same thing, this is just mu of K, right? But the issue is this is not continuous. Okay. Now, the great thing about metric spaces is if I have some compact set K, and this is my metric space X, and let's say that this is 1, right? So this is the real numbers. What I'm going to be looking for, I want to approximate this function by something. And the great thing about metric spaces is I have a notion of distance, so I can actually look at things like this, right? I can construct, so there exists a function, so I'll call it a phi, let's call it phi tilde. No, let's call it phi. of eta. So eta is somehow, I want to call eta this distance between these guys. Right, so it's like how far I am away. Such that, and then phi eta of x is going to be greater than the indicator function of k. Phi eta of x is equal to 1 on k. And then in some neighborhood, this is just an extra property, so the tubular neighborhood around eta of k, I could just say the ball. I want my function to be 0 outside of this, so right? So I don't pick up anything else. So phi eta phi eta right? Does everybody agree that this function, I mean, it should exist, right? It's not so hard to construct. Okay. Now the great thing is we did it from above, which just ends up being important. So notice that all we're trying to do is show that when I take the maximum of all of my measures, right? It stays bounded by whatever I'm converging to, right? So I don't lose mass for compact sets. So let's patch this together. So I know mu n converges weakly to mu, and I've constructed a phi tilde of eta, which is approximately the identity on k, right? So it has those three properties. And let's just use these together. So I integrate on x, phi tilde eta of x, d mu of x. And what should I do next? This is a mu n.
Then you apply weak convergence.
Yes, so we get weak convergence of this guy. What else can I say?
Oh, but you can also take the limit as eta goes to 0.
Mm-hmm. So I can do
and
that.
then apply monotone convergence or dominated convergence or
Mhm.
one of those.
So for this one, I kind of need that, right? So I know that, let's see. So this is going to be, dun, dun, dun. It's going to be less than or equal to mu of k plus some correction which comes from eta, right? So let's figure out what that is. So I know on this set, I'm 0, and on this set, I'm 1. So what I'm doing is I'm picking up this red region as my defect, right? Okay, and so what I'm doing is I'm splitting this integral, right, into the part where I'm integrating over k. I don't have to care about this part at all. So I'm splitting into integral over k and then the integral over this kind of annulus. So it'll be mu of k plus, and then mu of, it'll be b, some ball, eta of k, set minus k, right? So this is this red thing. It's the same here. Okay. What about for this part? So I've shown that the limit n goes to infinity of this guy, eta of x to mu n of x, is less than or equal to mu of k plus mu of b eta of k, set minus k. Okay, and actually I don't quite want to take a limit yet. I just know this. Okay. So really what I want to do is I want to get rid of eta in my expression, right? Then I can take a lim sup in n. So what I use is that this guy is less than or equal to. Well, I know that it's above this, right? It should be. Yeah, okay. Sorry, I don't know why I've been putting tildes, but it's whatever. This is going to be mu n of k, right? Okay. So what we've shown in total is when I take, so notice that while this guy has a limit, this guy might not. So let's just take the biggest possible limit I can take that it still exists. So the lim sup n goes to infinity mu n of k. This guy is going to be less than or equal to this guy. When I take a lim sup. Oops. Which I know is less than or equal to this. Which has no n in it, right? And I know that this guy is, so I take eta to 0. Lim sup mu n of k. Mu of k, like this. So we're good. Okay, any questions about that? I find it super helpful for these things. I mean, it can be a little weird just saying, oh, I have a general metric space. But in a lot of these scenarios, you just got to draw the 1D picture and then try and figure out what's going on. Okay. Great. If there's no more questions, I'm going to go on to 7, which I think is kind of fun. So let's look at 7 really fast. Okay, that's not what I wanted. Yeah, that's kind of annoying. Well, let's just read it from here. So what it says is the following. If I have a measure in the plane such that for all open squares that are measurable, there's a property that for alpha positive, there exists some alpha positive such that when I have 2 open squares that are translates of each other and their closures have non-empty intersection, then I can get a bound of one in terms of the other. Actually, in particular, what I get is the measure of the closed thing is less than or equal to alpha times the measure of the open thing, right? Okay. Our goal is to show that horizontal lines have 0 mu measure. Okay. Is that clear to everybody? So what's happening is I have a cube, I have cube Q, and then let's say I have some translate of it. This is a Q prime, such that their closures have non-empty intersection. Right, so that's this version. then what I can say is that mu of q bar, so the closed thing, is less than or equal to alpha mu of q prime. And want to show that L, which is equal to, let's say, a particular line, horizontal line, mu of L equals 0. Okay, so there's a couple reductions we can do to this statement already. So one is if I have a horizontal line like this, and I want to show it has measure 0, it suffices to show that only an interval of length 1 has measure 0, because I can patch them together, right? So I just use countable, I can split my measure a countable number of times, and I know that I can write the whole line as being unit chunks. So without loss of generality, the length of L has length 1, right? It's just, you can assume it's finite. So that's property 1. Another is our problem is translation invariant. So I can assume that it's actually just the one particular set. It doesn't really matter so much, but it's just something funny. So problem is translation invariant. So I can really pick this, whatever I want to show, I just have to show it about like this interval. So 0, 1 crossed with just the point 0. Right, just to simplify, I'm using symmetry to reduce my problem to something that's easier. Okay. And now can anybody tell me, like, how do I use this condition to help me show or get a good covering of my set?
Yeah, the thing I did was
Mhm.
you actually don't even need such a strong condition. You
Mhm.
actually can just take q and q prime to be equal, and then you get the measure of the closure of q is less than or equal to alpha times the measure of q.
Mhm.
And then I came up with a sequence of like dividing the line up
Mhm.
into yeah, I just came up with this sequence of open sets that go to the empty set, but where their closures go to the line.
Yeah, I see what you mean. Yeah. So let's look at that. I think I know what you're saying. So the idea is to construct cubes that cover L, right? So I have this 0, 1 line, and I'd imagine you did something like this, right? So I take cubes, their lower edge. So these guys are cubes of length like 2 to the minus n. So there's 2 to the n of them here.
Yeah, and the idea with using a 2 to the n is that each the n plus 1th collection of cubes fits inside the open cubes fits inside the collection of open cubes. So
yeah, so in general, yeah, that's why dyadic things are nice somehow. Just as a side note, because if I have a cube that's dyadic, so it's of length, so the length of the cube is 2 to the like j or something. When I subdivide like this, I get another cube, right? So you can think about a very nice covering of my line by the following way. So let's say I take this guy. So this is this is a covering of n equals 4. Sorry, n equals 2. Then what I can do is I can subdivide each of these cubes. So let me do this sequentially. So I copy this. For the n equals 3 case, what I do is I instead I subdivide everything like this. And I just pick these regions. Right, so this is how you would algorithmically construct this set. Right, so these are the things I care about. Okay, so let's call each of these collections of cubes. This is going to be Q at some level n. And then let's call this one the jth one. So this is j equals 1, j equals 2, j equals 3, j equals 4. Right, so j equals 1, j equals 2 to the n. So what I get is that mu, well, as sets, I should say, L is contained in Q, J, to the n, when I union over J.
And you take the closure.
And I had to take the closure because they're open cubes, exactly. Right, because otherwise I'm putting them right on the line somehow. Like this line is right on the boundary of these cubes. Okay, and so what I can start to do here is if I take the measure of L, it's less than or equal to this sum, Q, J, N bar, 2 to the n. But I know from my property above that actually every cube is a translate of itself, right? So I have this property for any cube, which is the translate. So in particular, I have that the measure of the closure is just alpha times the measure of the open thing. Okay, so that's gonna be this guy, Q and J. Okay, but these guys are now disjoint, right? Since they're open, and I put them right next to each other like this, they don't intersect at all. So I use the property of measures that this is actually just going to be the union of Qj. Okay,
And we also need an alpha.
and there's an alpha. Very nice. Okay, wonderful. So what do we do from here? So I've covered my set. I have approximated it by an open collection of things. Then, for a second.
Yeah. Then you take the limit as n goes to infinity, and using the fact that these unions give you a descending chain of sets.
Mm-hmm. Yeah, so these guys are decreasing, right? They're getting smaller and closer to the line. So I know that these guys converge to alpha mu of, and then what happens, they're never including the line, but they're getting asymptotically close, so they should be going to 0, right? I have a feeling that's true, but
Yeah, it is true because the y coordinate is strictly between 0 and 2 to the minus n.
yes.
So anything in the intersection would be an arbitrarily small positive number, which is not possible.
Mm-hmm. So this goes to 0, and I know by this decreasing, the first one's finite, they're finite measures. So I know that this guy goes to 0. Okay, and we're done. So we've shown that mu of L is less than or equal to 0. And it's a positive measure, so we're good. Okay, any questions about that? Okay, great. Well, if not, I think we're gonna end for today. And yeah, I will send solutions of that first problem I tried with it ends up using vitality, which I forgot about. But yeah, it should be, and next time we'll talk about integration and do a few more problems. Before we go, I have a few recommendations for things we could do. So the next section is about density and limits in LP spaces, which we haven't talked about, but it might be nice to go through and solve. Let's see. No, we talked about convergence and measure, right? So I would recommend in this section, so in 3, prove problem 2 and yeah, let's just try problem 2 for now. And all of these we'll go over next time, I think. And I'll be taking questions about any of the other measure theory things. Okay. So I just have one recommendation for this week. Okay. Very cool.